conservation of mass, incompressible flow, etc. And we will now try to see that given that we have incompressibility constraint kinematically. So we have to remember that incompressibility constraint is related to divergence of velocity equal to 0. This is the bottom line of the kinematic restriction related to incompressibility. Now, this itself will contain three velocity components in a Cartesian coordinate system UVW, in other coordinate systems, other notations, but more than one velocity component, whereas you have only one equation to deal with. So you have one equation to deal with, but multiple velocity components are there. Therefore, it may be convenient to use one parameter and express all these velocity components in terms of one parameter. So that is a parametric representation. So single parameter representation. So it is just for representation, not for solution of the velocity, because solution of the velocity is itself dependent on maybe several other things. For example, what is the force acting on the fluid in terms of the driving force, resistance force, etc. So just by incompressibility constraint, it may not be possible to find out the individual velocities. In some cases, in some special cases, it might be possible, but in general, without referring to the forces, that might not be possible. But the parametric representation should be possible, and to explore that, we will consider two different examples. So the first example is two-dimensional and incompressible. Two-dimensional and incompressible. So when you have two-dimensional, incompressible flow means this equation will be satisfied. Two-dimensional incompressible flow means only you have the relevant x and y components. So our objective is to convert this to a one parameter representation. So to do that, we may define a parameter psi, which is a function of x and y, such that u is equal to this and v is equal to this one. So when you have u equal to del psi del y and v is equal to minus del psi del x, what obviously you can see is that once you substitute u here, you will get this, and once you substitute v here, so these two will cancel each other, not trivially always, but trivially for the case where the parameter psi has a continuous second order partial derivative. If the second order partial derivative is continuous, then it doesn't matter. I mean, you can interchangeably first differentiate with respect to y and then x, or first with respect to x and then y. and the results will be all the same. And then these two will be identical with opposite signs, so sum total will be 0. And that is the motivation of choosing this parametric form. Keep one thing in mind, that the motivation is to satisfy this equation, number one. And number two, there is no restriction on the algebraic sign of any of these terms so long as sum total is 0. That means u could be defined as minus of this and v could be plus of this alternatively, but we have to define one of these, and that is why this is taken in this way. So this parameter psi is called as stream function. So the question is that, well, we have defined something as stream function with certain restrictions, but what is the origin behind this physical name of stream function? So to understand that, let us say that let us just write psi as a function of x and y, and just use the mathematical rule of the differential d psi, which is the sum of the partial differentials. This is just a simple mathematical rule, nothing more than that. So had there be function of n number of variables, there will be n such terms. Okay. So now what we will do is we will substitute this as minus b from the definition that we have just made, and this as u. So now if you set up a situation where we are trying to explore or see what does it mean if psi equal to constant. So when you have psi equal to constant, what it all means is d psi equal to 0. So d psi equal to 0 will mean that minus v dx plus u dy is equal to 0. And if you just rearrange it, it is dx by u is equal to dy by v. In the two-dimensional plane, if you recall, this is nothing but streamline equation. This is equation of the streamline. If you recall one of our early derivations, dx by u equal to dy by v equal to dz by w. And therefore, this is the streamline in the two-dimensional plane. So psi equal to constant physically means that it is a streamline, and that is why the name stream function. Now, what is the connectivity between the streamline concept and a stream function concept? That is something which is a little bit more subtle than this. First of all, streamlines are very generic definitions without any restriction. That means we are saying that it's an imaginary line which at some instant at every point the tangent is representing the velocity at that point. So in that way, streamline is a generic concept, but the stream function is not a generic concept, it is a restrictive concept. The restriction is that we imposed these two very important assumptions. Two-dimensional plus incompressible. Okay, so when we have this two-dimensional plus incompressible flow, this is what which has been the restriction. So in that way, when we say equation of streamline, we don't normally keep a restriction, but when we say definition of a stream function, this is what the restriction that we have put here. In a general way, a three-dimensional flow could also be, incompressible flow could also be represented by some parametric form. But now that is a little bit convoluted, because then we have to look into each of the planes and maybe represent one parameter for each plane rather than a single parameter for the general three-dimensional flow. For compressible flow also, you could introduce similar parameters. For example, for compressible flow, you could define, see, for incompressible flow, U was defined as this. For compressible flow, instead of U, you can define rho U as this, so that your objective of satisfying the continuity is satisfied. So in a way, for compressible flow also you can extend with adaptation of the definition. Three-dimensional also you could extend, but a single function may not work, because there will be three terms in the equation and it will be difficult to find one single parameter that will satisfy that. But plane wise, you can have a two-dimensional type of the equation and it will be representable by some parameter. But the way in which we are defining the stream function here, that is very much restrictive to two-dimensional and incompressible. And therefore, the connectivity between stream function and streamline, we are exemplifying for only two-dimensional incompressible flow. For any other general flow, streamline is definitely there, but it cannot be connected with stream function, because the stream function will not be defined in the way if this restriction is withdrawn. Okay. So this is one parametric representation. The other case, we will consider maybe another example. So the other example that we will consider is example 2, irrotational flow. So irrotational is a English word which means that there is no rotation. So when there is no rotation, the angular velocity of flow, this has to be a null vector. And angular velocity we have earlier defined how the angular velocity of flow can be described, and derived an expression of that in terms of the different derivatives of the velocity. So remember that the angular velocity is half of the vorticity vector. This is, I mean, all these things we have discussed earlier, so I'm not wasting much more time. And the vorticity is the curl of the velocity. So what it means is that for irrotational flow, the curl of the velocity vector is a null vector. Right. So this is a hallmark of the flow has no angular velocity. That is the physical hallmark. Mathematical hallmark is this. Now, if you look into a vector calculus identity, I mean, forget about whether it is fluid flow or whatever. So a vector calculus identity. See, this is how mathematics connects physics. So curl of grad of a scalar function is a null vector. So this phi is just a scalar function. This is a vector identity. This doesn't understand any physics. It's just a vector identity. So now, if you put up a comparison between these two equations, and no, this is actually an identity, not an equation, but this is an equation for irrotational flow. So when you are satisfying both of these, this will always be satisfied, but this is only for irrotational flow. So our conclusion is that for irrotational flow, at least you can express the V as the gradient of a scalar potential. Okay. So this scalar potential, again, so you have now seen that one of our wish lists which was there, that for a three-dimensional flow, still we are interested to find out a parameter. For irrotational flow, no matter whether it is two-dimensional or three-dimensional, we have not put up any restriction here, 2D or 3D. So for a general irrotational flow, doesn't matter 2D or 3D, you are able to express the velocity in terms of a single parameter. So in terms of the components, so this parameter phi is called as velocity potential. And in fact, the flow where the velocity potential exists, see, in all flows, velocity potential will not be existing. Only for irrotational flow, it will be existing. And if the velocity potential exists, it is called as a potential flow. We will have one chapter towards the end of this course where we will discussing about the potential flows. So when you have the velocity potential existing, what does it physically implicate? See, if you have say V as gradient of phi, so let us say this one. So let us say we have two different points, 1 and 2. And the difference in their x coordinate is say delta x. So if you integrate this equation, you will get u2 minus u1 is equal to, so if you integrate with respect to x, we cannot just say phi2 minus phi1, but in other words, in a simple way, because I will illustrate how you calculate the difference in phi between 2 points. But conceptually, what I'm trying to say, and possibly I'm trying to oversimplify a little bit, but trying to give you a concept. The mathematical thing I will talk about in a moment. That the change in phi due to this change in x doesn't depend on how a fluid particle possibly has gone from 1 to 2. Maybe it would have gone by different paths. So the points are important, endpoints. So this, I mean, those of you who have studied thermodynamics, this is known as point function. So the hallmark of a point function is that it is path independent. And what makes a function path independent is a nature of the field where the path has no influence. For example, let us say, I mean, I'm just giving a different example, altogether not connected with fluid flow as such. Let us say you have a small block sitting here. Now there is another high level to which you have to take the block, and the height is h. So you could take the block by this path, whatever. But the potential energy that you gain out of this in GH is not independent of, not dependent on what is the path that you have followed for taking the block there. The reason is that the gravitational field G that you are talking about here is a conservative field, and therefore it doesn't depend on the path by which you are moving the block from the lower height to the higher height, and that is one hallmark of a conservative field. That is a conservative force field will have the work done, because you can represent it in a different way. The potential energy you can represent as work done against gravity. That is what is the energy gained at the end. So that work done is independent of the path. It can be said for potential energy related physical concept, because gravity field is a conservative force field. Similarly, when we say that we have irrotational flow, what we are meaning is that there is a conservative field that is describing the velocity, and therefore conceptually we are expecting that there is no dissipation. See, if you have different paths, but the matter, the concept doesn't depend on the path, what it means is that different paths will give what, in terms of say a very common school level physical understanding, different paths will give different friction. So what it means is that therefore we are talking about a concept where friction doesn't matter, and for fluid, friction is synonymous to viscous effect or viscosity. So that means that these are possibly, we will study later on in dynamics of fluid flow and conform, that these are possibly representing situations where the viscous effects are not important. Otherwise, this kind of conservative field description is not physically going to work. I mean, mathematically, of course, we can define it for irrotational flow like this. Now, let us put up a comparison between the two parametric forms that we have just learned. So I'll just maybe try to sketch a table by which I will try to summarize that. So the psi concept, for that we required two-dimensional plus incompressible flow. That was the binding restriction for mathematically expressing its definition. For the velocity potential, it is irrotational. Doesn't require any restriction for 2D and 3D. Now, just to put up a comparison between the two parameters, parametric forms, we need to find out cases where both are defined. Then only we can put up a comparable platform or comparable basis for that, and then that common restriction is two-dimensional plus incompressible plus irrotational. So two-dimensional plus incompressible plus irrotational. The advantage of I should not say advantage. The reason for taking this restriction is that you can then define both of these. So then, first of all, we have seen that psi equal to constant represents a streamline. We have to see that what phi equal to constant represents, which we may say as a equipotential line, because this is named as velocity potential, but how does it relate to the streamline? So to understand that, we will simply use the differential rule that talked just now. So psi is a function of x and y. Remember, I mean, let us say that it's because it's two-dimensional. Let us assume that everything is taking place in xy plane. So this is minus b dx plus e dy. So if you have d psi equal to 0 or psi equal to constant, that will give you this right hand side equal to 0. That means dy dx for the psi equal to constant lines is equal to v by p. So dy dx is a very important parameter for any curve from your basic calculus knowledge, all of you know, because it represents the slope of the tangent at a given point, say x comma y. Now we are also similarly interested to see phi equal to constant. Yes. And phi is a function of x and y. So d phi is equal to sum of the partial derivatives. And if you see the definition of the velocity potential, this is u and this is v. I mean, you can refer to the previous page of the note. So what it means is that if you have d phi equal to 0, that is phi equal to constant. And for this, you have dy dx for phi equal to constant is equal to minus u by v. So when you have that, so dy dx for psi equal to constant and dy dx for phi equal to constant. We can just, I mean, let us just multiply these two at the common point, obviously, at the same point x comma y. So the same uv will be there. So this is v by u into minus u by v. And the general temptation will be to straight away cancel v and cancel u and get minus 1. But we have to see whether this general temptation of cancelling works or not. So first of all, it works clearly when u v these are not equal to 0, because then you can safely cancel things. And if u v are not equal to 0, you are able to cancel things. What we are coming up with is a condition that in calculus we have learned regarding the relationship between the slopes of the tangents, common tangents, tangents at the common points. So if you have, say, a family of lines with psi equal to constant, say this is psi equal to psi 1, this is psi equal to psi 2, and this is psi equal to psi 3. We are trying to see that what is the geometrical relationship between, say, perhaps phi equal to phi 1, phi equal to phi 2, and phi equal to phi 3. So for that, what we have done, we have identified a common point x comma y. So this is one common point, just as an example. Then by dy dx at that common point, we are physically meaning a tangent to the curves, and so these become straight lines, and this is m1 and this is m2. So if you have m1 m2 equal to -1, that means angle between the two straight lines is 90 degrees. Okay, so this doesn't mean that curves are perpendicular. It simply shows that their common tangents are perpendicular, and so this is called as orthogonal curves. So for curves, we do not say perpendicular. So this is a matter of terminology, but perpendicular is something that that is to be there in our mind because the tangents are perpendicular. There is nothing called as perpendicularity of curves, and that is why the name orthogonal is used. So they are orthogonal curves, and the advantage of orthogonal curves is that you can generate one of these functions if you know the other function by using the orthogonality. So if you have two-dimensional, incompressible and irrotational flow, and by some way you have this, then the family of orthogonal curves can be generated, and those will represent the phi equal to constant lines. In computational fluid mechanics, this can be one very simple way of generating grids to solve a problem. I mean, just to give you a basic perspective, say if you are solving a differential equation numerically, most of you have heard at least about a finite difference method. So what you are doing is you are having a domain. You are say having some sort of grid lines, and these grid lines will convert this domain into certain grid points at which you are writing some algebraic difference equations instead of the differential equations. That is what is the finite difference approach. So here the grid lines are straight and orthogonal. So you can similarly generate for a curved geometry, straight grid lines will not work. For a curved geometry, you can generate these lines which are still orthogonal but are curves. So in that way, for solving computational mechanics problems, this can help in generating grids. So this is an offshoot. It has directly nothing to do with this kinematics concept, but this is an indirect advantage or indirect benefit that we are getting. But we have not yet completed the definition, because we have to see that what happens if this restriction is withdrawn, that is either u equal to 0 or v equal to 0 or maybe both are 0. So if either of u and v are 0, then you can see the great trouble here is you have division by 0 and or 0 by 0 form. Say v is 0, and that means this this cannot work, because if the operation itself becomes indeterminate. The indeterminacy is the strongest I mean, or the most obvious, you can say. I mean, it is strong for all cases where there is division by 0 or 0 by 0 form. But it is the most obvious when both are 0. I mean, and when both the velocity components are 0, it is a physical point in the flow called a stagnation point. So stagnation point is a point. Again, look into the English word stagnation. Means that the flow is completely stagnated. That means it is not moving, 0 velocity. So if there is a stagnation point, then at the stagnation point, this orthogonality concept you cannot apply. For other cases where individual u and v components are 0, there also you cannot apply. And you can apply only for cases where u, v are not equal to 0. And so you can summarily say that at least streamlines and equipotential lines in a two-dimensional incompressible irrotational flow, they will be orthogonal to each other everywhere, but physically there is likely to be a stagnation point in the flow, and there it will not be applicable. Now we will try to look into a bit deeper issue about the differential equations that will govern the variations of these functions phi and psi for the special case that we have considered. That is two-dimensional, incompressible, and irrotational. So just to separate or segregate the calculations, I'm just putting it in a tabular form, but the restriction is two-dimensional, incompressible, and irrotational.
Good morning, ma'am.
So now phi was defined how? And what is the definition of this in terms of psi? So this is the definition of the phi and psi, which we can apply for this one. Now, while putting up this definition, what was the consideration? So when we put up this definition, the consideration was irrotational. Two-dimensional and incompressible. So two-dimensional and incompressible has to be this two-dimensional plus incompressible, because we are at the end trying to put all these three restrictions on the definitions of phi and psi. So when we do that, we can simply substitute this definition of u and v and put it here.
Because not all the sums will take 5 minutes, some sums will take 1 minute, some sums will take 2 minutes. Yes, you check, so what?
So when you have this, so what I have done is I have put in both the definitions of u and v in terms of phi in the two-dimensional incompressibility constraint. So this is a two-dimensional template of a more general three-dimensional equation, which is called as Laplace equation. That anybody who has done a preliminary level calculus, college level calculus course will know the Laplace equation template, and will also know its impact in various areas of physical applications. So here it is fluid mechanics. In electrostatics also, the electrical field will in some cases, not always, satisfy the Laplace equation. Now you have to keep in mind that this Laplacian operator, this so-called Laplacian operator, this is actually a three-dimensional operator, not a two-dimensional operator, but that two-dimensional variant of this can be applied for cases where it is 2D. So then this will not come into it. So this is the Laplace equation in two dimensions. Now let us come to the issue of the definition of psi. So first of all, we have used two-dimensional and incompressible flow for parameterizing this equation. So what we have not shown, or what we have not considered, is whether this is irrotational flow or not. So if it is irrotational flow, this should be applied, or that will lead to, in the two-dimensional case,
Sir, what we do revision? Today's exam. Sir, please do division.
So for two-dimensional case, this will lead to this condition. Irrotational flow means curl of the velocity is a null vector, and for a two-dimensional flow where only UV components are there, this is what it will lead to. We have actually derived this in various ways. I mean, this is actually angular velocity. In fact, twice of angular velocity in the xy plane. If you could remember the derivations that we have made earlier. So now if you substitute this u and v.
Sir, please, what type of revision it is?
So this is also like del square psi equal to 0.
Yes, practice.
So you can see very interestingly, when you have two-dimensional incompressible and irrotational flow, both these functions of x, y, they are satisfying the same template equation. It's the Laplace equation. That means, in a different way, if we solve these differential equations,
Okay, sir.
solution of these differential equations will give us how these are distributed. How we are going to do the solution is a different matter. It could be analytical solution, numerical solution, whatever it is. But if we find out a solution of these equations, that will give both of these as functions of x and y. Now, apparent conflict will come that same equation we are solving, and then we are claiming that these are two different functions. That thing is not very non-obvious, because although the equations are the same, the boundary conditions are different. The boundary conditions for phi, say let us say you have a domain, whatever, you may have the same equation if all the all these conditions are satisfied, but the boundary conditions on phi and boundary conditions on psi, they will be different, and that will actually drive the orthogonal solutions. So not the same solutions, but orthogonal solutions, although the same template equation is actually guided not by the equation but by the boundary conditions. Okay, so let me just stop the presentation here, and or rather close the writing pad. So we have a few minutes, and because this is almost towards the end of the kinematics chapter, we have discussed all the concepts that I wanted to discuss regarding the kinematics. In the next class, I will try to solve a problem which will cover many of the things that we have, a single problem which will cover many of the things in the kinematics chapter to give a connectivity, and then it will be the next chapter that we will enter into, that is the dynamics of in-visit flows, that is fluid dynamics, where viscous effects are not important. And before that, maybe if you have some questions, queries, doubts, etc., you can express. We have another roughly 5 minutes before closing this class, and we can discuss. But just one important point before I forget: the coming Monday, I will not be taking the class. So coming Monday is off time for you at this time, 8 to 9 a.m. No class on advanced fluid mechanics for the coming Monday. So please make a note of this. If later on I forget to remind you through ERP or whatever. Okay. Now you please, if you have questions, you can raise your hand and share whatever question you have. So just let me ask one thing. I will, of course, share the solution guide or the answer key to the first so-called practice test or mock test that we had. But let me know that was there any kind of difficulty in approaching the questions conceptually.
Sir, it is easy.
Anyway, we have one question first. I will take that. Whoever has raised hand can tell the question, and then we can come to this point. Yeah, if you have question, you can tell.
Yes, after multiplication, we
somebody raised hand.
Whatever we get, we need to move the point.
Exactly, see who the person is, but somebody has raised hand, so you can please tell your question.
Sir, what question Asim is asking, I know the answer.
Okay, so
yes, after the normal answer,
now can you tell that while trying to answer the question in the first mock quiz, what I mean, if there was any issue which sort of put you in a little bit of sort of I mean, I would say not a very applying a straightforward approach to solve the problems. What was that which is something that you want me to discuss? I can always put up a solution, and I will do that within the next few days, so that you can see the solution. But solution is always differentiation and integration, nothing more than that. But what is that that problem solving key step that somehow you thought that perhaps you did not get it when you are solving the problem, if at all something is there?
Sir, we were familiar with, hello sir.
Yes, sure.
Sir, we were familiar with that Cartesian coordinates, and we were not at the time familiar with that cylindrical coordinates. So we
Uh,
faced that
see,
problem.
see the important hallmark of the problem that I uh, asked you to solve there doesn't require any expression of cylindrical coordinate system actually to remember. So if you, I mean, if that is what I wanted to conceptually discuss. So you have a velocity field where you have r and theta components. So that much you know polar coordinate system from your uh, you know, uh, school level, that what is a polar coordinate system, r theta system. So now equation of streamline, how it is defined? See, look into the vector form. It is defined by coming from the fundamental derivation dr cross velocity vector is a null vector, right? So only thing that you have to do here, the velocity vector, you have the r theta components. The dr that is in terms of the position vector, it will have r theta components instead of xy components. In xy component, what will be the dr? It will be dx and dy. That all of you can understand. In r theta, it will be dr in the r direction and r d theta in the theta direction. And all of you know that a small r in the theta direction is r d theta. So simply replace those dx and dy by dr and r d theta, and use that dr cross v is a null vector, and put up the determinant expression for the cross product. That doesn't depend on any coordinate system, and you will be able to get the equation on the streamline. Okay. So now you tell, does it require any understanding of any formula of
Sir, and
a
for that acceleration part,
no, acceleration is acceleration is if, you can just differentiate find out the relevant components, the time derivative, the derivative along r and derivative along theta, and the same thing you can apply. You have to keep in mind that the major difference that we are talking about between the Cartesian and this polar coordinate system is that when you are talking about the y direction, in the Cartesian we talk about dy, in the polar we talk about r d theta. Okay, so you can make adjustment with those, and remember that these are, because all these exams are going to take place online from now onwards, and I want to get you familiar with this. You are, see, because you are giving online exam, one fundamental thing is that you are having access to internet, otherwise you cannot connect with me, right? That is the first most obvious thing. So because it is an online examination, I mean, if you are not familiar with some expression or something, you can as well search in Google and find it out. See, I have absolutely no restriction in this, because problem solving is a life skill, right? I mean, in the later part of your career, when you will be doing a job, nobody will tell that you cannot consult book, you cannot consult Google or whatever. But you have to solve a problem, which is for whatever purpose. So I do not want to give you a lesson which is such that if you, I mean, the only check is whether you can remember or mug up or that kind of thing. So if you feel that something there is an expression from the internet which you want to borrow and use, just use it. But the basic principle while converting from the xy to r theta is what I have just indicated. And actually this basic principle will lead to the more formal equations. If you look into the formula for the cylindrical polar coordinate systems of everything, you will see that the formula is actually constrained by these basic principles. Nothing more than that. But you can always look into that. I mean, in books it is there, in internet it is there. For so many other things, you see, you make search in the internet and figure out. I would encourage that you use this more for educational purpose. There are so many
Yes,
you know,
sir.
excellent good educational materials. You make use of these, not just for your studying, even for all the exams or quizzes that I will be taking. You will be free to use that. There is absolutely no problem in that. Anybody else has any question? So if not, I think let us close this meeting. So close this class. We will meet again on the coming Tuesday.